Next is Priscila Moreira from University of Notre Dame, presenting on generative adversarial networks for paper analytical devices.
Okay, thank you for having me in this SciTech and Friends Research Symposium. It's a pleasure to be here. My name is Priscila Moreira. I just started as a graduate research assistant at the University of Notre Dame, where I started to research in AI and machine learning, more specifically with applications in digital forensics. But previously, I was working as an intern at CRC, the Center for Research Computing, and Notre Dame also, where I could work on these pet projects that I'm going to talk about today. So I'm going to talk about generative adversarial networks for paper analytical devices, which work I made under the supervision of Christopher Sweet. So the outline, I'm talking about a little bit of what is a PET, what is that? And then a little bit of GANs, and then the solution we propose to tackle the problem and next steps. Okay, so paper analytical devices for short pads are cards made of paper that we can use for quickly and cheaply decide whether a drug or medicine is in that is present on that. So it's made of lines, as you can see in the image. Each line is composed of a reagent that you can produce chemical fingerprints to give us an idea of if it's the correct or not the medicine. Okay, so how it works? You can take pharmaceutical and swap in the cards like horizontally, and after some 5 minutes, you have the reaction happen, and then this will be the fingerprints to decide for a specialist, right? For a chemical specialist, to decide whether the drug is present or not in that substance. So first of all, why this is important? Unfortunately, in some place in countries that are not so well developed, we have this type of fake medicines. So, for example, in Africa, the data set is coming from Africa, the middle of the data. So they have this issue there. So it's very important to tackle this problem in these scenarios, for example. And you can think also the pads can be useful in scenarios where police would like to decide that component, that substance is illegal or not, for example. All right, okay. Oops. So the project was initially the solution they proposed a solution using computer vision for that, convolutional neural networks for classify the paper, the image of the pad, and they published that in 2016 with an initial accuracy of 96%. Just to have an idea, the human specialist it can perform the task with 97%. To have an idea. So when I came to this project with more experiments and more data, we could improve the performance to 98% around. Okay, but the project has a dynamics situation that the new medicines, the new pharmaceutics are coming, and the specialists, the chemicals are trying to figure out new good reagents for that and build new pads. And also they can change this line. They can change the reagents. They can find better. So we have constantly new devices. But we have a problem with data, right? Because as I told you, the data came from Africa, for example, and we don't have easily access to this. So it takes time to have a lot. You know that deep learning with convolutional neural networks, they need a lot of data to perform well. So the idea is to process data augmentation with GANs to tackle this problem. So generative adversarial networks, right? For short, GANs. First of all, they came from 2014 by Goodfellow, the first proposed framework. And since there, it came. It's impressive with how the performance of this type of models are getting better. In minutes, for example, super resolution and colorization, and in data augmentation, as we are trying to tackle this problem here. So the state of art for GANs are the SciTech 2. So these people do not exist. So you can access this link and see different people that are generated from GANs. Okay. So, but what is a GAN, right? We have GANs are generative models. In comparison to discriminative models, discriminative models, the goal is to divide the space, the features. So we have features as inputs, and we need to decide class as an output. And we need to, the model needs to model the probability of the features given a class, okay? So the generative models, the task is a little bit different. We want to provide data, we want to generate data. So the feature is the output of the model, and the input is basically noise. And if you want to do a generation conditional to a class, you can use a class also. So from noise, we have features or images, or if you are working with time series, you can have a time series or sound or video. So here we want to model the probability of X, or probability of the features. Okay. So the general framework we have deep neural networks. We call generator that receives as inputs random noise, and then we have X hat that is in this case it's an image that's a fake sample, and then we have another classification, another deep convolutional neural networks called discriminator, and then we have also as input for this discriminator real samples of X. So as inputs of the discriminator, we have Y hat that will, in this case, a class that will say that the image came from the generator or came from the real data set. And the goal of the discriminator is to distinguish between fakes and real samples. And the goal of the generator is to make the fakes look like the real samples. So this is the general model, okay? But how to train that? It's a game of minimax. So let's say how to train the discriminator, because they are training in different ways. So the discriminator receives real data and the fake data that was generated by the generator. And then we have the y hat, and we'll compute the cost of this y hat. Okay, for example, we can use a loss like BCE, that binary cross entropy, and calculate the cost using the labels for real and fake, because here we have two class as inputs, and then we are back propagating this for the parameters of the discriminator be updated. So this is the step for the discriminator training. And for the generator, we only use the fake samples. So here the discriminator will not learn anything. It will just be used to get the output, the feedback. So once we in this phase when generator is learning, we will have the feedback from the discriminator that in this case we will set all the labels for real, even we are given as an input for discriminator fake image, because the generator wants to fool the discriminator. So we will set the class for real. So with that, we update the parameters of the generator. So it's two-phase training, and the idea is both generator and discriminator to get better, but they don't. They need to have similar skills, because if, for example, the discriminator is a simple neural network, will reach better skills than the generator, but this is not good for the learning. So we need both being good or at the same skill level. So here is the architecture specifically for the PAD project. This is the generator part. So we are given it's a simple architecture, different from StyleGAN 2. That's a very huge one. And the idea is to give a noise. In this case, we are work with 100 numbers, random noise. And we are upsampling this noise until we get an image from this size to 266 by 266. And 3 is the RGB, so it's an image, right? So idea is from the noise, pass through all these layers and get an image. As you can see here, we have for each convolutional 2D transpose layer, we have better normalization and liquid ReLU. It's very important to have this normalization. And without that, it's impossible to produce image, and the liquid ReLU is very important because we want, in this case, the negative part of the neurons, right? So if you just use ReLU, we will have 0 values. And then the discriminator is very simple, but because the discriminator just needs to classify, right? It's a classifier. So it will take an image and decide at the end with a value that it will be the probability of the image be fake or not. Okay, so we use sigmoid, simple like that. And here is some results along the steps. So you can see here in the left image, like noise, basically noise, because we have as input noise. There's a point here. We have a lot of pads in the same rectangle, right? So you will see as I will pass this. So in further steps in the training, we start to see some information. So the generator starts to learn and produce something that reminds a bad image. And then finally, we have like 4 by 4 pads here. and in 10,000 of steps. In this case, we use a lot of images actually. In comparison to our data set, we have 293 images for penicillin procaine. That's a medicine. Okay, so see more details what we are generating here. So I put here a synthetic image that we are generating for this pharmaceutical, and a real one that is similar but it's not the same image. So we are able to produce this kind of image that an expert can say, okay, I can say that is reaction for penicillin procaine. We had this feedback from the expert. So more results about that. We have different type of resolution, because when we received this data, it came from a lot of pre-processing steps, and it can be buried or damaged. So the generator is learning these features from the pad. So in this example, I'd like to challenge you to say which column is real, which column is synthetic. I know you are not expert in this, but so let's say you have that. So the results, they were very impressive for the expert, from the chemistry department. But what happened, the idea of using GANs here was to augment the data. So once we have this, we would like to improve the performance of the previous classifier they had. Okay, and what happened? We couldn't improve this with, for example, 15 images per class, right? And that's the idea. They are like, okay, we have this amount of images. Are you able to keep the performance of 98% of the classifier? So no, the answer now is no. But we have some ideas to improve the next steps. This, for example, I found that we had probably mode collapse in this method we use. So mode collapse occurs because the data, the real data, they are multimodal, right? It's not like a Gaussian, well-behaved. So we have a lot of peaks in the distribution of the data. And when you have that, it's easy to the learning process of the GAN get stuck in one of the modes. For example, for one class, there are groups of type of image. So the generator learned how to, it's like a minimal local. So he learned how to fool the discriminator, focus on one mode only, one peak. So we found this problem of mode collapse. So there are ways to tackle this, and they are next step. Also, now we have StyleGAN 2, the one that I show you with beautiful images from fake faces. Now they have a framework to apply for different data sets that is not only for a face. And we are about to test on that also. Also, this whole work brings to me the intention of research and the disentangles this space, or the latent space. What is that? The noise that I show you as input for the generator is part of we call latent space. If this latent space, after all the process of learning, you'll be like mapped for the features from the data set. If this latent space is very entangled, or in other words, it's the different features are not separated in this space, you you were not able to control the individual features. And my area of interest now is to research on that disintegral Z space. Now that I start with the research as a PhD student. So another challenge here is how to validate these synthetic samples, because we have in GANs, we have the known metrics like FID, that's range exception distance, that based on another deep convolutional neural network that is called exception, but the results are not so meaningful for this case. So we need to tackle this problem also. And here are some reference that I mentioned, right? And that's it, thanks. I don't know about the time.
Great, thank you, Priscila. Does anyone have any questions for Priscila?
Yeah, I just have a simple question. So firstly, Priscila, great work. It's an interesting application of computer vision. I'm really interested in this. And yeah, I guess I missed it. I just want to confirm. So in the first slide, you just told us that the initial accuracies were around 96%. Then you actually improved it to 98, right? So I just wanted to know like the intuition behind it. So the previous baseline, which was there, were they using GANs as well, or were they using some different pre-trained strategies, or what kind of models were they using? And like, how did you lead to using GANs to improve it? I just wanted to know the intuition.
Okay, you mean before the 98% accuracy?
Yeah.
They were just trying basic augmentation like brightness, some stuff, but for classification, the model is based on CAFENet.
Okay, so like the pre-trained models, right? They're using pre-trained models? Okay.
Oh, no, it's from scratch.
Oh, okay, learn from scratch. Okay, got it. So for the GANs, I believe you weren't using pre-trained models. Like you have to train GANs from scratch, right?
Yes, scratch.
That's interesting. Nice. Thank you so much.
Thank you.
Hi, I also have a question. This is a very impressive work. I love the samples that you were able to create. And I heard that training GAN models is very difficult. And could you talk to your experience, how you were able to create such a good samples and what techniques you perhaps use? And then I'm also interested in what you said about incorporating this disentanglement of the latent space and using maybe variational autoencoder. So I would like to understand more how those parts will work together, the GANs and variational autoencoder. Thank you.
Okay, you're welcome. So yeah, it's very challenging to train because you can have only noise, and if you are with the wrong parameters, hyperparameters, you will get only noise, right? It's very easy to get stuck in some point like that. So it was just tweak between the optimizations, and as I told you, I noticed that batch normalization is very, very important after each convolutional 2D transpose. As I told you, the liquid ReLU is important also. Just a ReLU is not a good function to produce image in this case. I didn't tell, but I tried different GANs, right? Not only the DC GANs, that is a standard GAN, as the one that I show you is a standard GAN. But there are again that use the class as input also. In addition to the noise, you have the class called ACGAN. The results with ACGAN wasn't so good as with DCGAN, but I think it needs more experiments, more tweaking. But it would be better to use ACGAN. Why? because with ACGAN, we have just one model for every class in the data set. With the DCGAN, we have for each class one model. You understand? So it's not a good, I think, practice in that workflow for them, because there I think we need to switch this architecture to another one. But ACGAN, I know that doesn't work so well, because I have made some experiments. I had a web interface with showing for the experts different image for different GANs, and at the end I found that the GAN performs better for the expert view point of view. Yeah. The other question. Okay. Variational encoders. Yes. Variational encoders are better in this work of disentangle the Z space. You're right. That's the direction. When I started with this project, I didn't know anything about generative models, so I started with GANs. Then I learned how to do variational encoders, and then I get started with the PhD, and this semester. But the idea is to combine, I think, variational encoders with GANs in some way to produce that. But I need to say that StyleGAN needs to be experiment first. Why? Because it has improvements that capture the characteristics that variational encoder has and GANs has together. So